arene synthesis basically. And here the starting element is nothing but the amine system. This is your aromatic amine system. Mostly the famous compound is your aniline here. Now, if you check this one actually, here the starting material is nothing but this one. Actually, this is not the starting material, but actually you have to convert this aniline system in a diazonium system. And that is why, you know, famously from this to this conversion, we have to go through this intermediate. This intermediate is called your benzene diazonium salt. Actually, you can synthesize this benzene diazonium salt directly with HNO2. But since HNO2 is explosive, you all know that. That's why aqueous NaNO2 and diluted HCl under ice cool condition, that is your 273 to 278 Kelvin temperature, you will first get this intermediate. After that, the second step is actually the Sandmeyer. The second step actually Sandmeyer is you have to use your copper halide and your halo acids like your HCl, HBr, etc., or might be your HCl. Okay, so by this process, you can get not only the chlorobenzene or bromobenzene, but also the cyanobenzene compound, basically. So here one question which is very important: how can you convert actually aniline into bromobenzene? So obviously you have to start aniline, you have to go through the intermediate. That intermediate is nothing but your diazonium salt. This diazonium salt. Okay, as I told you, you required actually HNO2, but since HNO2 is explosive, directly we can't use this HNO2. Instead of this, we can synthesize in this reaction by the addition of aqueous NaNO2 and diluted HCl under ice cool condition, that is 0 to 5 degrees centigrade temperature. And obviously, you will get this intermediate benzene diazonium salt. And the second step, this step actually, the reagent is nothing but CuX, or sometimes teachers used to write that Cu2X2, and this is HX. Here X might be, as I told you, might be your chlorine, might be your bromine, or might be your cyanide. So by this process, you can get chlorobenzene, bromobenzene, or cyanobenzene. Okay, so this is the best step to get your aromatic halide actually by this process. Next reaction is the modified Sandmeyer. This is called also the name is called Gattermann reaction. Here actually you will use, instead of this CuX2, this copper powder, and the remaining part will be same. That is your HCl, HBr. This will be same. That means the starting material, as usual, the intermediate, what you used in the last reaction, that is your diazonium salt, and this diazonium salt under this one is producing, you will get this one. What is the advantage of this reaction? Why we are choosing this Gattermann reaction so much over Sandmeyer? Because the possibility of actually, in the last case actually, we are starting with aniline most of the cases, and we are producing fasting the diazonium salt. And the main difficulties for the formation of the diazonium salt is the ice cool condition. Not only that, the percentage yield of this reaction is not actually significant. So that's why instead of this, if you are using this reaction for in terms of better percentage yield, okay, and this will be a easier, more economical or percentage yield reaction. Any question, anyone, please? Okay, no question. Now, by this process, as I told you, we can synthesize by these two processes. As I told you, we can synthesize chlorobenzene, bromobenzene, and cyanobenzene, not fluorobenzene actually. So, to form the fluorobenzene, to produce fluorobenzene, you have to utilize another actually reaction. And that reaction is another name reaction. And that reaction is famously known as your Ball-Schiemann reaction. In the Ball-Schiemann reaction, we will run again, same like this diazonium salt. So in this first stage, from this aniline, we will generate first diazonium salt. So basically aniline, the starting material will be as usual aniline, but this is not your Ball-Schiemann. Here you have to produce this NaNO2, HCl, ice cool condition, you will first get the diazonium salt in this case. N triple bond N, the plus charge on this first nitrogen. And here if you are using chloride, it will be Cl minus. In the next stage, the attacking agent is fluoroboric acid, HbF4. And this fluoroboric acid, this H plus and Cl minus in this stage eliminated, and you will get this intermediate. So what actually used here, this HbF4 and HNO2 simultaneously, this is actually not used. Actually, you have to synthesize first this diazonium salt, then you have to react with this HbF4, you will get this one. And whenever you will put little bit amount of the heat, that is in terms of energy, it is written here, you will, the N2 of this system gets eliminated, and the BF4 system actually uh, dissociated as BF3 and F will introduce in your benzene ring. By this way, you can get the fluorobenzene component. Okay. Okay, and this reaction is very important. Most of the time, it's asked that how you will synthesize fluorobenzene from aniline. Sometimes the question is asked in terms of how will you synthesize fluorobenzene from the benzene diazonium salt. These kinds of question usually asked for the exam. Okay, now the next reaction is the Finkelstein reaction. Why this Finkelstein reaction is so crucial? We have to understand. Actually, we know that whenever any kinds of uh, chlorobenzene or bromobenzene, if we want to synthesize, then if we want to any chloro system or bromo system, that is your methyl chloride, let's think about your methyl bromide, etc. Then if you are starting with your iodo system, actually respect to the iodo, chloro and bromo, their nucleophilicity is greater. As student, you know that, and this will obviously, this Cl minus and this Br minus in any non-polar solvent will participate in SN2 reaction, and obviously from the backward side easily eliminate I minus. As usual, you know the nucleophilicity always follow the F minus greater than Cl minus greater than Br minus greater than I minus. The nucleophilicity is actually basically the charge density of the system. As you know, from the fluorine to chlorine, size increases, but the charge on each and every system is -1. So I can say that then obviously charge density of the fluorine is higher than chlorine, than bromine, than iodine. So obviously, if the system is made by Ri system, then greater nucleophile Cl minus and Br minus in a SN2 process can easily remove that I minus. So these kinds of substitution reaction, by this substitution reaction, you can easily get the chlorobenzene, bromobenzene compound, your chloroalkyl system, bromoalkyl system from any iodo system. But it is very tough to synthesize any alkyl iodide. Okay, that's why for the formation of alkyl iodide, special treatment is essential, and that treatment is nothing but your Finkelstein reaction. Here, notice student what actually usually done. Here, Rx is taken your any alkyl halide. The halide component is made by chlorine and bromine. That means here the chloride bromide are higher nucleophile respect to I minus. So what is the target? The target is we have to replace, and the way is you have to put more density, and it is possible by inputting one ionic halide instead of any kinds of normal covalent halide. So here we use sodium iodide or potassium iodide, and by this way iodine ion is completely free, and charge density due to its higher density means I minus ion density actually easily can eliminate to form the Ri, and obviously the NaX gets eliminated by this process. So this is the importance of the Finkelstein process. Normal for any process, we can easily synthesize chloride or bromide, but it was tough for the iodide. That's why this Finkelstein method, by using ionic halide, the solvent is sometimes acetone little required. Water is not actually, you can use water or you can use ethanol. Why? Because I minus present in the system. If you are using OH minus in terms of water, or let's think about you are using alcohol, let's think about methanol, mean methoxide will be the competitive nucleophile of the I minus system. So better, that's why if we use acetone here as a solvent, then this kinds of competition is omitted. So better that I'm suggesting, or Finkelstein suggested that if we are using ionyl halide in a little polar medium or small polar medium, that is the acetone, these kinds of replacement or these kinds of substitution become very easier. This is the main motto of this reaction. Now, next one is your SWOT reaction. As I already told you, the nucleophilicity order follows F minus greater than Cl minus greater than Br minus greater than I minus. So for the formation of any kinds of alkyl fluoride from any alkyl halide, that is chloro or bromo, no requirement of the ionic halide. That's why if you are using silver halides, that is your silver fluoride, mercurous fluoride, antimony fluoride, or cobalt fluoride, all these are metallic fluoride or covalent fluoride, then this reaction will give you the fluoro compound, and fluoro compound means your alkyl fluoride system. So alkyl chloride, whenever heated in the presence of any metallic halide like silver fluoride, this is not exactly ionic like sodium iodide, or your mercurous fluoride or antimony fluoride or your cobalt fluoride, you will get the fluoro component, means fluoro alkyl fluoride from any alkyl chloride or alkyl bromide system. Okay, any confusion? Any student have any question, please? Any student, any question? No. Okay, so I'm proceeding for the next. Next reaction is from the same chapter, that is your haloalkane haloarine chapter. This is the important reaction, that is Wurtz reaction, Fitting reaction, and Wurtz-Fittig reaction. These all are important reactions. And by this reaction, we can synthesize any kinds of alkyl from any alkyl halide or from any aryl halide. We can simply synthesize one hydrocarbon component. So for the first one, that is your Wurtz reaction, for the Wurtz reaction, the substrate component is nothing but your alkyl halide. So whenever this alkyl halide is taken with metal sodium, and this is your XR, two molecules is taken physically, and obviously you should have to take one non-polar solvent and also aprotic solvent, and that is why dry ether is the best choice. Why? Because last day during the discussion of electrochemical series, I told you sodium has the property of actually reaction with water and with the water under cold condition. Not only that, sodium can react explosively with aerial oxygen also. Okay, that is why whenever we are thinking about the reaction of sodium, we have to put the solvent, we have to put dry ether as a solvent. This will be the best choice. And here the X system and the sodium, 2 mole of this X and 2 mole of the sodium, simple just eliminated as 2NaX, and you will get your desired product R and R. And what is the specialty of this reaction? The specialty of the reaction, the product here in the product, carbon-carbon bond is formed. This is the number one. And number two, here you are getting alkane from any your corresponding alkyl halide. So for this case, mostly bromide, iodide, chloride, these kinds of system you can use as the starting material. Okay, any confusion, any question? Okay, so now I am coming for the fitting reaction. The reaction mode is same to same. Here the both system are same, means the starting material substrate are both same, that is Rx and Rx, both are alkyl halide. When both system are the aryl halides, I am taking chlorobenzene, you can take chlorobenzene, bromobenzene, iodobenzene, whatever your choice. Okay, and same metal sodium, and again chlorobenzene again, then simple in the same dry ether medium as I told you earlier, because we have to stay out from any kinds of explosion, that is the reactivity of sodium, and our target is to directly sodium will react with this chlorine. Simple fact. And by this way, 2 sodium and 2 chlorine, 2 mole NaCl will be replaced or actually eliminated from the system, and the remaining part, this benzene system and this benzene system, or you can say 2 phenyl ring basically, will form one or joined by one carbon-carbon bond and form biphenyl system. One biphenyl system. You can see here this same thing when aryl halide system, it might be chlorobenzene, bromobenzene, iodobenzene, you will get biphenyl as the product in the Fittig reaction. So Wood's reaction, this is for purely alkyl system, means alkyl halide involved. And for the Fittig reaction, it is purely aryl halide system involved. Is it okay? Any confusion, please? Anyone, please? Any student? You can raise your hand. No one. Okay. Now I am coming for the mixed one. That is Wood's Fittig. Means some student may think that, sir, this is well okay for the Woods, it is for the aliphatic system. And whenever I am thinking for the aromatic system, it is well okay. But think about when mixed system present, that means both aliphatic and aromatic system present, then what happened? And that's why Woods and Fittig combinedly suggested that or synthesize that when we are taking the same aryl system, means halo, let's think about your, I am taking chlorobenzene, bromobenzene, iodobenzene, and same sodium metal is taken, and same, let's think about alkyl system taken. Simple, in the dry ether medium, this X sodium and this X simple two molecule of the sodium halide will get eliminated, and your product will be this benzene, and from this side any alkyl group. So phenyl group and alkyl group will be marked by this way. So these kinds of mixed formation of your hydrocarbon, that is aromatic and aliphatic, both system involved, that is your Wood-Fittig reaction. Now student, you can question me, sir, what is the importance of this reaction? Or what is the relation with this exam? Because sometimes these kinds of conversion you will face. And for you, I am writing this conversion. So conversion is sometimes the question will say that prepare, I am writing on it, or you can see here, prepare toluene from chlorobenzene. Prepare toluene from chlorobenzene. These kinds of question may ask, or sometimes these kinds of question may ask, chlorobenzene given, okay, then okay, you have to fulfill this question mark and you will get the final product as following. You have to just write what are the component will be replaced this question mark. So simple, as I told you in Woods-Fittig reaction, the starting material you have to use, one is your chlorobenzene, and your target is toluene, na? So right part is methyl system. So another part should be one methyl system, and you can use chlorine here, and just put 2 sodium as usual, okay? And you will get in the dry ether medium, and you have to impose little bit of heat. This condition is not mentioned here. You have to put little bit amount of the heat, not too much excess heat is essential here, because hydrocarbon present here, and you know the boiling point of the hydrocarbon are not too high. That's why excessive heat actually not essential here. So chlorobenzene plus 2 sodium, as usual, right part was your CH3 toluene system. So this is the second component. In the presence, in the dry ether medium, in the presence of heat, you will get your desired product toluene. Any confusion, any question? If you have, please you can ask me. Any question? Any question, please? No. Okay. Now, if you have not questioned anything, you can go through this problem. The problem mentioned in the bottom side. Look at this. Here the question is, what is the Q? Means here the one benzene plus Cl2 APCl3 T Na ether Q. You have to fulfill this reaction. You can take the help of your teacher and solve this question. I am just giving one hint that in the first stage with APCl3, this Lewis acid, this APCl3 Lewis acid will take one chlorine unit from the Cl2 system, because Fe system is actually APCl3 system is the example of Lewis acid. Lewis acid means the component having lack of electron density, or actually by this acceptance of electron density, it can satisfy this next octet. Normally from the theory of the covalent theory octet, it is assigned that Okay, normally it is assigned that, but it's not 100% true because it's the system of the D block. That APCl3, whenever coordinated with the, or actually connected with the fourth chlorine, then it will satisfy its octet, because around the AP system, 3 chlorine unit present, and sometimes teacher explain in terms of d orbital vacancy. Whatever the theme, the AP system wants to grab the electron density from the chlorine. And that's why when it's happened in the first stage, Cl plus will generated from it, and the lone pair density when it is trapped by the AP system, and this component electron density will be switched towards this. And by this reaction, Cl plus and FeCl4 minus on Fe, this produced. And this Cl plus will be easily trapped by this high electron rich benzene ring. And that's why in the first stage, that means as P, you will get the chlorobenzene. You will get the chlorobenzene. And in the next stage, look at this sodium diether, you will get the same Wurtz-Fittig reaction. So your final desired product will be the option number B, toluene. Please try in your home. And if you have any question, you can ask also. Anyone? No. Now, next reaction. This reaction is associated with alcohol chapter, haloalkane, haloarines chapter. Okay, both associated. So this reaction is called Friedel-Crafts reaction. Here the substrate is nothing but a 1 pi electron rich system. And pi electron rich system means substrate should be one benzene and connected with one electron rich system. Here that's why we start with either benzene. Here that's why we start with either benzene or your anisole system or with chlorobenzene, because here chlorine contain lone pair which can participate in the conjugation with your phenyl ring by density. That means it is nothing but the plus R operator. On the case of anisole, it also contains lone pair. That lone pair also participates in conjugation with the benzene ring. And that means this OCH3 system is also the plus R operator. And here benzene ring itself present, which carries your 6 pi electron, that is 3 pi bond. So we can say that this Friedel-Crafts reaction is nothing but the reaction happens in the pi rich system or pi density rich system. Since it is pi density or electron density rich system, this reaction will run via electrophilic substitution, or you can say here electrophile get trapped by the benzene ring. So simple here in this case, substrate is a pi density rich system, that is your might be benzene, might be anisole, might be chlorobenzene, might be even toluene, no problem. Okay. Now here, generally we use any kinds of Lewis acid like anhydrous aluminum chloride. Okay, no. Put. Anhydrous aluminum chloride might be your APCl3, might be your PbCl2, might be your ZnCl2, might be your BF3, any Lewis acid you can use. Okay, but selectively in this reaction, Friedel-Crafts means scientist, as per his scientist name, they use anhydrous aluminum chloride. Here the same logic, that aluminum is connected with 3 chlorine, its octet is not achieved, and that is why here it will trap one chlorine system, one chlorine, any kinds, anywhere you can see this chlorine system present. And in the first stage, Cl3 will trap from this CH3Cl system, any kinds of, not only CH3, you can use any alkyl system also, RH system, that's why you can use any RCl system. The lone pair of this RCl will be trapped by this aluminum because of this factor of Lewis acidity. So in the first stage, this sigma bonded density will be switched by this impact, and by this way you will get EAlCl4 minus, and by this way Al actually satisfying its octet, and by this way one R plus means one electrophile is generated. Here for the CH3Cl system, if we introduce this CH3Cl system with anhydrous aluminum chloride, then you will get this AlCl4 minus system, and Hello, any problem? Any problem, anyone, please? And CH3 plus system. Here the CH3 plus acts as an electrophile. Since it is plus charge species, so benzene pi density, here the benzene ring pi density, here the benzene ring or phenyl ring, whatever you are saying. This phenyl ring pi density actually will trap this CH3 system. Okay, and I am not giving the mechanism here. Basically, where it is replaced, if I am thinking this benzene, normally in the benzene system, student, you know that all carbons are connected with each one hydrogen. So there is no extra place other than replacement of the hydrogen as H plus. So basically, in this case, I am writing here the benzene will lose one H plus, and this will trap this CH3 plus, or you can say R plus. Okay, and this eliminated H plus will trap this Cl minus from AlCl4 minus. That means this AlCl3 not only acting as a Lewis acid but also acting as the catalyst. It participates in the reaction and eliminates in the reaction. This is not only a reagent, this is not only used for the formation of this R plus, but also in the first stage it is introduced or okay inserted, and the last stage is eliminated. Means role is like a catalyst. Okay, so this H plus and this AlCl4 minus means Cl minus will trap to form the counter product or the side product at HCl, HCl for each and every case HCl. So this is the reaction. You can say this is nothing but an electrophilic substitution type reaction. Okay. Any question, anyone? Any confusion? Any argument? Whatever you can ask me. No problem. You can say me also. No. Okay. Now I am giving two special cases where for this anisole system I am giving for this anisole system and I am giving for this chlorobenzene system. Because whenever you are starting this reaction with chlorobenzene and anisole, you will get two different products. Why? Because on this impact of this substituent group. As I told you, both of the group are plus R operator, both of the group of the plus R operator. Plus R operator resonance is always operate via pi bond. And you know this resonance are distance independent effect. That means it will enhance the electron density in the ortho position and the para position via conjugative structure in equal extent. That means by the resonating effect, you can segregate between majority and minority of the product. Okay. So another factor that is your the sigma bonded factor that is called the inductive effect is mainly responsible for this minority and the majority. So here the chlorine is more electronegative than this is adjacent connecting carbon. So this is minus R operator. Minus R operator means it will drag the electron density from the carbon. That means from this system it is dragging the electron density. And you know pi bond formed from the sidewise overlap and area of overlap is very low. On the contrary, sigma bond is actually nothing but your head-on overlap. So area of overlap is greater. That means sigma bond is more tightly held bond, whereas the pi bond is very feeble or loose bond. And that is why you are noticing that pi bond is actually participating in the reaction, not the sigma bond. But here, inductive effect is operating via sigma bond. So the closer position, ortho, the closer position, this is your ortho position, and the opposite side or the further side is your para position. So from the ortho position, by the minus I effect, this chlorine or this same OCH, this oxygen will drag electron density more. So comparatively, the para position will be more electron rich. So the corresponding para will be your major product. Similarly, for this anisole system, para will be your major product. But student, if you are starting with this CH3 system, means toluene system, and you are, hello, yes, toluene system, and you are giving same thing CH3Cl anhydrous aluminium chloride. Here the solvent may be your carbon disulfide, maybe your nitrobenzene. Okay, solvent is not important for your exam, so student don't bother about it. Okay, if you can remind them well, otherwise you can skip, no problem. So basically, nitrobenzene or CH2, any solvent can be used here. So here, two products also possible by this. As you know, this CH3 will operate the hyperconjugative effect. And by this way, in the ortho position and in the para position, it will enhance the electron density in equal instant. Hyperconjugation is nothing but it's called no bond resonance, which operates via sigma as well as via pi bond. So by this impact in the ortho and in the para position, electron density enhancement happen in equal extent. But as I told you, this hyperconjugation, resonance effect, by these two effects, actually electron density enhancement or decrement happen in equal extent in any position, means ortho para position, I'm saying. That means it is distance independent effect. On the contrary, sigma bonded effect, that is your inductive effect, is distance dependent effect because it operates via sigma, which is tightly held at bond. So this is carbon, no electronegativity difference, but hydrogen has the electronegativity 2.1, while this carbon has 2.5. That means this group actually is not an electron withdrawing group, but this group is electron pushing group towards this ring. So by the plus I effect of this group, the closer position ortho will get the more electron density. So the corresponding product means corresponding ortho product will be your major product. Any confusion, any question from anyone? Because these kinds of questions sometimes asked when question is little bit tricky. You are saying that this question is little tricky or question is hard. Actually, the question is not hard. Actually, question is this kind of. Okay. Any question? Anyone? Any JNB? JNB? I think JNB. Pemanku JNB means JNB Tawang joined. Hello, any question from JNB Tawang? You can say by typing. Okay, no question. Well, so I am going on the next reaction. Here, actually, the reactions I have taken from your sadhana paper, and second one is taken from your CBSE paper, sample paper. Okay, so please check this reaction. Student, try to sort out this matter because our main target is to get the marks. Okay, so match the reaction given in column 1 with the name given in column 2. These kinds of reaction first. Column 1, column 2. This is paper is from Sadhana. You can check there from also. So the first reaction is nothing but we already read this reaction here. This reaction here. One system is arine system. Second system is aliphatic system, means haloalkane system. So this is nothing but mixed, not exactly phytic or not exactly Wurtz. This is your Wurtz phytic reaction. So you can connect this one with this. And the second reaction, the benzene system means aryl system, and it is two molecule use. That means both system are arine system. And you are getting the product that is your biphenyl. So this is completely phytic reaction. Okay, and we already read this one. As I told you, ammonia to X formation, this is not your Sandmeyer, but from this intermediate step, this is your Sandmeyer reaction. So this reaction from your intermediate, that is your diazonium salt, whenever you are using Cu2X, actually if you are not using HX, no problem, because this X and this X if are the same component. I am saying that if this is your chloride and this is your chloride, if you are not using HX, no problem, you will get the product and you will get chlorobenzene as the product. But if there is mixed, then the X will come from this CUX system, not from this ring, means intermediate system. Please student careful about this kinds of tricky question also. So this is simple example of your Sandmeyer. And the last reaction, CH2H5Cl NaI diacetone. Boardwalk is not visible. Hello? One is complaining
Sandip da.
about boardwalk is not. Ah, yes.
সন্দীপদা, তোমার বোর্ডটা দেখা যাচ্ছে না, তুমি একটু ক্যামেরাম্যানকে বলো একটু ঘোরাতে।
আমার বোর্ড তো
তোমার মানে তুমি যেটা লিখছো না বোর্ডে, সেটা বোঝা যাচ্ছে না।
হুম
তুমি একটু বলো মানে বোর্ডের দিকে ক্যামেরাটা ফোকাস করতে।
আরে ক্যামেরাটা দেখো বোর্ডে অলরেডি ফিক্স করাই আছে।
ওই এখনো
That's
তো বোর্ডটা তো বোর্ডটা
actually I am writing on the board and total screen is sharing right now. On the last day, there was separate setup. Right now, it's a both setup are same.
ঠিক আছে, তুমি একটু দেখো। হ্যাঁ, ঠিক আছে।
It's fine, Sandip, I think.
Sivan sir, it's a fine.
Because the board is visible to us, the students, and your video may not be directly visible, but it is not required, no? Because the main content is visible to us.
And yes, my voice is available now.
Yeah.
Okay, no problem then. Okay, just notice that if board and my writing is visible or not. I am not matter. Actually, my voice should be there.
Content is visible.
Okay, that's all good. So whenever I am taking C2H5Cl with sodium iodide, as you know, this reaction is the Finkelstein as discussed. So please choice option accordingly, A, B, C, D. I already marked it. And if you are facing still problem, you can take the help of your teacher. Now, in the second problem, this reaction is already discussed. This is your Fiddlecraft reaction. This is also from the Fiddlecraft. I already discussed here. Now, this one I will discuss a little bit later. So please wait somewhere. Now, second one is the Fiddlecraft second part, that is the acylation part. So same mechanism, same thing. Here, one pi density rich system, that is any arine system, reached with a pi density, might be your directly benzene, might be your chlorobenzene, might be your anisole system, as usual, I told you. So here, if you are starting with the component RCOCl, you can use also RCOX. This chlorine, instead of chlorine, you can use also bromine. Okay, but it's a little bit problem for the iodine and fluorine. That's why I'm not recommending this iodine system and fluoro system. That's why most of the Fiddlecraft reaction generally run with chloride system or bromide system. So it is most commonly written as CH3COCl. Students don't think that bromide system will not participate or will not go in this reaction. It is possible also with the bromide system. So whenever any pi rich system or pi density rich system will be attached or will go in the reaction with an acyl system. Acyl system means your RCO plus. This system, okay, instead of only R plus what you noticed in the last case, that is your Fiddlecraft alkylation. The same mechanism will follow. Instead of this R plus, RCO plus will be connected. Now here in the starting material, your starting material is nothing but CH3COCl. Whenever it will react with anhydrous aluminium chloride, then in the same fashion, this chlorine will be attached with the aluminium by its Lewis acidity factor, and this CH3CO system by this disconnection, it will create this, okay, CH3CO plus this cation, or sometimes this is called electrophile. This is better term. So this CH3CO plus system will be trapped by this pi density of this benzene ring. So you will get the single product for the benzene system because all the 6 carbons are symmetrical. As you know, as your teacher also explained, that C6 type of symmetry present in this system, and all the carbon are called equivalent. So you will get one single product. But whenever you are taking chlorobenzene or anisole with your starting element, then by the plus R effect of the chlorine and by the plus R effect of the lone pair of the oxygen, the ortho positions and para positions become electron rich. On the contrary, respect to this, these meta positions are electron dwarf system. So ortho positions and para positions will get this electrophile. So we will get two products as usual. But here, the majority minority will not change because majority minority depends only on the substituent group present initially, and it is on its inductive effect, as I discussed. Since chlorine and OCH3 both are minus R operator, so from the closer ortho positions, they will drag more electron density. So respectively, para position is more electron rich. So para product will be your major product, because sometime in the exam, student be careful, because they usually ask write the major product only. So don't be confused. Always focus on the initial substituent present in the benzene ring and consider its nature. Don't bother about the resonance, only bother about the inductive effect. Whatever the resonating system present, hyperconjugative system present, they are not actually bothering on the majority means or minority means orthopara position. Because I already explained, you can also check the exactly class 11 resonance structure. By this resonance structure means Placer effect, from the ortho in the para and in the ortho positions, electron density enhancement happen, not in the meta. So meta product will not form here in a major minor. Will form, but it will be very little. Let's think about in a 100% product. If you are considering, let's think about this major product is from 60% and this is 30%. The meta product will form. That will not be zero, but it might be 1%, 2%, 3%, etc. Any confusion, anyone? Any confusion, anyone? Okay. Okay. Now I am proceeding for the next reaction. This next reaction is associated from the next chapter, that is alcohol phenol ether chapter. And we already switched from that chapter because the last reaction was the common reaction of your haloalkane haloarine chapter and your alcohol chapter. So this is from your alcohol chapter. So look at this. The first reaction is the Reimer-Tiemann reaction. Here in the Reimer-Tiemann reaction, substrate is phenol. Substrate, the starting material is the phenol. Starting material is your phenol normally. Okay. If you are taking OCH3 system, etc. system, then these kinds of conjugation practically this intermediate formation possibility is quite difficult. And if you are changing this base also, then different product you will get. That is why selectively you have to use this chloroform and NaOH. Even you can get or you can use this KOH. If you will give the KOH, then ortho product will not form. Okay, this is not included in your syllabus, and student, I am not also discussing about it. Okay, I am discussing only about the reaction which is involved in your mentioned in your book. So Reimer-Tiemann reaction, the starting material is actually phenol. You are and the substrate which participate in the reaction is chloroform and NaOH. Basically, in this reaction, what happened? The chloroform, the CH, Cl, 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 3 chlorine present, and these 3 chlorine by their high minus I effect, okay, makes this hydrogen is highly acidic hydrogen. And that is why, since in the medium NaOH means base present, the OH minus will trap this H. And in the first stage, you will get this CCl3 minus system. And actually, this CCl3 minus system is Cl, Cl, Cl. And in the next stage, the Cl minus will be eliminated. And most of the students, I think, know one intermediate, reaction intermediate might be singlet or might be triplet. I'm not going on singlet triplet right now. One intermediate is formed. Please careful about this intermediate. This intermediate is known as carbene intermediate, because sometime in the short question or MCQ question, they usually ask that 4 options might be given there, that carbene intermediate is formed in which reaction? Reimer-Tiemann, Kolbe, Woods, or Woods fitting. You have to choose the right one. The answer will be Reimer-Tiemann. That is why I am mentioning here this intermediate. So basically, when the phenol is reacting with this chloroform and NaOH, then in the first stage, basically, by this NaOH, the phenoxide form, and this phenoxide will attack from this ortho position, and it runs via concerted mechanism. That means in this stage, before this stage, here one between this ONA and this CH system, one 6-member ring is formed. If you are taking this potassium hydroxide, then the ring, 6-member ring, are not stable. That is why the ortho product will not form. Generally, you know that if this reaction is following an electrophilic mechanism pathway, then since OH contain lone pair, it will enhance the electron density in ortho and para position. Then and also OH is minus I operator. So para product will be your major product. But in reality, we are getting the ortho product. What is the meaning of this? It means that in this particular intermediate, there is a concerted pathway. That means one weak hydrogen bond actually formed between this ONS system and this CH2Cl2 CHCl2 system, and that's why in the next attack with NaOH, when this ClCl both are eliminated, this NaOH is aqueous NaOH basically, you will get this CHO as the product. Means you will get in the final hydrolysis, after hydrolysis, this ONA will be replaced as OH minus, and you will get your final product, that is your salicylaldehyde. So all those students who are facing some little bit hazy or little bit confusion about it, please, I'm giving the fresh form, what actually initially was. The fresh form was this. So you started with the starting material, phenol, with the reaction with CaCl3 with NaOH, and intermediate is formed. Intermediate is not essential for your reaction, for your exam. You have to write substrate, reagent, and only the final product. You have to mention in the reaction number 1 CaCl, this one, and in the final state H plus. You have to write only the salicylaldehyde as your product. Okay. Do not go in the KOH, NaOH confusion and think about don't think beyond it. Only about the reaction. Basically, why I mentioned this the intermediate, because sometimes short question appeared in the exam. Sometimes tricky question may ask. Sometimes if instead of this chloroform, if anyone is using CCl4, carbon tetrachloride, after this hydrolysis, in this stage, you will not get this intermediate. You will get CCl3 intermediate, and after hydrolysis means C, OH, 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 because you know between chlorine and the upcoming nucleophile OH minus from this NaOH, the OH minus has greater nucleophility. So this OH minus will replace this C chlorine to form COH, OH, OH. And these kinds of OH are called geminal you know about geminal triol. This is an example of geminal triol, and this is unstable. So basically, in the next stage, water molecule gets eliminated, and you will get the product means C double bonded O OH. That means if you are starting with CCl4, you will not get this product. You will get instead of this COOH this product. Is it okay? Understand? Understand? Any question, anyone, please? Okay. Now, some student may ask that, sir, it is difficult, na? Because in the Riemann-Tiemann reaction, whenever we are using this CHCl3 means chloroform, we are getting salicylaldehyde. We have to change the substrate CCl4 to get this salicylic acid. Is there any reaction, sir, by which we can directly get from phenol to our desired salicylic acid? Because salicylic acid is a good component in actually medicinal aspect. That's why this salicylic acid is so crucial. The solution is your Kolbe reaction. So when this same phenol, same NaOH in the alkaline medium, we are reacting with CO2 and H plus, means carbon dioxide gas in the presence of acid catalysis. You will get the final product of this one, which is called salicylic acid. Sometimes one short question may ask like this: what is the IUPAC name of the salicylic acid? Okay. Now, since in this ring OH present and COOH present, both group present, and this COOH group, this is the main component group. Okay. That's why the name is from 2-hydroxy, not from 2-carboxylic like this. Okay. So 2-hydroxy benzoic acid system. Actually, I think everybody knows about this nomenclature. The nomenclature part actually was nomenclature and all means from each and every chapter properly explained by Ramesh sir in the second day. I think student already grabbed that one. I think these kinds of thing are not confusive right now for our dear students. So one question, this question is very important. I took this question from the CBSE paper. And the question is, identify the following reaction. These kinds of question may directly will give you this diagram, and they may ask you what kinds of reaction is this? Woods reaction, Etter reaction, Ramatrim reaction, Kolbe reaction. I think students know it. What is the exact solution of this? Because I already discussed. Now I am coming the next slide. This is apart from your alcohol, the last part uh, that is your ether part. Mainly this reaction, ether part contain mainly this reaction. That is your Williamson ether synthesis. So Williamson ether synthesis is so crucial because this part contains two things. One is the Williamson direct synthesis and one is some mechanism associated with it. That's why it's so crucial. Please follow it. So basically Williamson ether synthesis is the process by which you can produce both symmetrical and asymmetrical ether. That's why this is so important. And this process actually runs via SN2 pathway. This is most important. And here the starting material is nothing but one, your aryl system or your alkyl or aryl halide system. And the second is your alkoxide system. And this alkoxide actually participate in the SN2 reaction. But student is, you are very intelligent and careful, I know it. This should be, always should be aliphatic system. Otherwise, if you are using aromatic system here, then backward attack, that is the SN2 attack, is not practically possible. Each and everyone knows it properly. But this system means our system might be replaced by the AR system because there is no problem with this one. But obviously, the rate will be different because if you are using aliphatic system, let's think about I am using the starting material as CH3. Sorry. If you are using, let's think about CH3 O minus, and I am second one, I am using this phenoxide system. Then you know this CH3 has a tendency to operate the plus I effect, and this phenyl ring, on the contrary, here the minus charge of this oxygen will participate in the conjugation with this benzene ring. So possibility of the electron donation will be lower for this system and higher will be for this system. And that is why I am saying that if you are using alkyl system or aryl system, the reaction will go on, no problem. But there will be difference in reaction rate. Aryl system will give you the slow reaction. On the contrary, this aliphatic system will give you the better percentage yield from that context. So basically in this case or in this reaction, we will start with one alkoxide. Alkoxide might be sodium or might be potassium alkoxide you can use, and halide system might be chloride, bromide, iodide. And you know, since this reaction is running via SN2 pathway, so obviously for the SN2, better the leaving tendency, greater will be the reaction rate. That means RI system is the best choice over RBH system over RCl system, because I system, iodide, has a greater radius than bromide than chloride. So iodide will be the best leaving group here, respect to bromide and chloride. Any confusion from this particular part? Why we are choosing these kinds of substrate? Because the reaction is running via SN2 pathway, and in this Williamson ether synthesis, your substrate is nothing but alkoxide. It might be aliphatic or it might be aromatic. Will participate in SN2 reaction. That means it will attack from the backward side, and by this way, the nucleophile X minus will get eliminated. So here let's think about, I am starting with a reference of this sodium ethoxide and ethyl chloride. Then sodium ethoxide means the oxygen minus will attack from the backward side, and this chlorine will get eliminated. And by this way, this ethyl, oxygen, ethyl means this ether will be formed. Now you can change the situation of the ether. Now if you want to get the asymmetric ether, then you have to choose the substrate accordingly. Let's think about, I am starting with the substrate CH3, CH2, O minus means this alkoxide, plus the remaining part is, let's think about CH3Cl. Let's think about. Then this oxygen will attack on this one, chlorine will get eliminated, and This is following your SN2 pathway, simple, and the product will form CH3, CH2, O, CH3. Now notice, in the last case, you got this CH2O, CH2O, C2H5. In C2H5 in this side, C2H5 in this side. So this is the example of symmetric ether. This is the example of symmetric ether. Symmetric ether means when both sides of the oxygen, the groups are same, they are called symmetric. On the contrary, when the both sides of the oxygen contain different group, this is methyl, this is ethyl. Okay, they are called asymmetric ether. So this is the good process for the ether formation, by which choosing the proper substrate, you can get the symmetric ether as well as asymmetric ether. Any question, anyone? Anyone, any question? Anyone, any question? Well, no. Now, student, please try to solve one particular problem. Now let's think about you have to synthesize this ether. In the exam, generally these kinds of questions asked. You have to synthesize this ether. CH2, CH3. Then what should be the starting material? What should be the starting material? That means this bond may clipped or this bond may clipped. Then if think I am marking this bond as A, I am marking this bond as a B. Now let's think about the left hand side clipped. Then scenario will be this one. Okay, then might be this, and the right hand side will be HO, or let's think about Na plus O CH2. This one. Okay, and on the right hand side is might be benzene, your O minus, Na plus plus CH3, CH2, Cl. Which one should be the best choice? Please, JNB will try. JNB, yes, Tawang, you can try. JNB Tawang, which one will be the best choice for the preparation of this particular product in the Williamson synthesis? Okay, I'm giving some seconds. Well, okay. So for this formation of this one, this is one choice, this is the second choice. Now, if I am thinking about this one will attack from the backward side in SN2, then this nucleophile will be, get a repulsion from the pi density of the benzene. Okay, so this substrate choice is not a good choice for this synthesis. But if you are choosing this one as your starting material, then O minus, if it's giving the attack from the backward side, then this chlorine get easily eliminated. Since this one is aliphatic system and this is your 1 degree carbon, because this is the group, this chlorine is the group, here the carbon is connected with only one carbon. So this is 1 degree. And as you know, 1 degree alkyl halide is the best choice, or methyl halide is the best choice for these kinds of SN2 reaction, where 2 degree, 3 degree, any aryl system are not the good choice for SN2 reaction. So we have to go with the second one. Here is the question. You can take the help of your teacher and try to solve. Now I am coming for the next slide, next reaction. Next reaction, this is from your carbonyl chapter, that is the Rosenman reaction. This Rosenman reaction is applicable actually for the formation of both sets of any kinds of aldehyde, not the ketone. You can synthesize any kinds of aliphatic, aromatic, whatever, the carbonyl, the aldehyde system only. Now here the starting material is normally your acyl system, might be your ArCOCl or might be RCOCl, anything, no problem. And here actually the palladium is the catalyst present here. Mainly this hydrogen is replaced, this chlorine is replaced by the nascent hydrogen produced in this process. Actually, here hydrogen gas is not directly used. It is we are getting this hydrogen from the solvent. In this case, solvent sometimes is your xylene. Solvent might be your quinoline. Okay, they are the good supply. Quinoline. Okay, so here actually this hydrogen with this palladium actually metal directly it is used on that time because this is Rosenbaum is nothing but modified Lindblad as you know it. I think your chemistry teacher explained it also properly. So this palladium actually produce this nascent hydrogen because this nascent hydrogen is crucial to break this polar COCl bond actually. Okay, and by this replacement, two hydrogen atomic hydrogen form, and that will replace one Cl as HCl as your byproduct, and the remaining part means ArCO and hydrogen, RCO and hydrogen as this one form as your product. But please careful about it. This reaction is solely by this reaction you can get solely the aldehyde only, not the ketone. Now, Stephen reaction is same thing. Mechanism is not essential. Only you have to go with the reaction. Now, for the by the Stephen reaction, same aliphatic, aromatic, both you can get the means aldehyde, but you have the starting material is nothing but one Lewis acid, stannous chloride with HCl. In the first stage, same reaction form, SnCl2 will trap the chlorine, okay, same Lewis acidity theory, and will generate the nascent hydrogen, which will attack this polar RCN system, okay. And by this way, in the first stage, this imine is formed, that is your 2-degree amine, and in the next hydrolysis, the RCHO and corresponding ammonia gas is formed. If you are using, let's think about HCl as your hydrolyzing agent, this one is HCl, then instead of the ammonia gas, you will get the salt of ammonium chloride. Okay, this is the simple process. Now here one question is famous question, convert benzoic acid to benzaldehyde. So student, you have to first use this SOCl2 for the chlorination. Okay, by this SOCl2, you will get the COCl, benzoyl chloride, and in the next reaction, Rosenbaum step, you will get the same benzaldehyde as your product. Simple, this kinds of reaction will come. Okay, sometimes this reaction will come as ABCD. You have to think and you have to utilize all these reactions properly on that particular concept. Now, the next reaction is your Etard reaction. By Etard reaction is the reaction the same. You want to produce the aldehyde, okay, not the ketone. But here starting material is a hydrocarbon, not your any kinds of acyl chloride or aliphatic chloride, etc. So by this Etard reaction, the starting material is your normal toluene is mostly used. And here chromyl chloride, CrO2, Cl2, and one non-polar solvent like CS2 is used. The intermediate is not essential, not us, okay, normally. Okay, and you will get in the final stage of acid hydrolysis the same benzaldehyde as the product. Okay, benzaldehyde as the product. Now, to solve these kinds of questions, let's think about in the exam, they will ask you, write or convert benzene into benzaldehyde in one step, either in one step or in two steps. So whenever it is saying in two steps, in the first stage, you can use the Friedel-Crafts reaction. By this Friedel-Crafts reaction, from the benzene, you will get the toluene. This is Friedel-Crafts we already discussed. Now, from this toluene, you can utilize the Etard reaction for the two-step process. Now, let's think about the question is asked that convert benzene into your benzaldehyde in single step. Then only when out is the Gattermann-Koch reaction. Okay, the parallel reaction is Gattermann reaction. Actually, I know, I think it's not mentioned in your book, but I will say a little bit about it. So Gattermann-Koch reaction is nothing but when the benzene gets attacked by the one Lewis acid in the presence of Lewis acid, aluminum chloride and CuCl trace amount required, CO and HCl basically. Then the same logic here, aluminum chloride in the first stage will trap this chlorine as usual, you know it, and this COH, this part will actually inserted with the pi density of this, because in this case same thing, electrophile will generate, electrophile will be trapped with the benzene, okay, trapped by the ring density of this benzene. Now, if you are using instead of this CO as HCN, that means HCN, HCl, Anhydrous aluminum chloride is your starting element reaction or starting material with the benzene. You will get the same product, but the reaction name on that case is only Gattermann. Only Gattermann. The difference of Gattermann and Gattermann coach is only two things. One is this HCN, this is gas but poisonous. Though CO is also poisonous, but HCN is more poisonous. This is one thing. And second thing, most importantly, the product percentage yield. The Gattermann coach is actually giving you better product because of the CO actually. Understand? Any question, anyone? This question is very crucial. Convert benzene to benzaldehyde in one step and two step. Any question, anyone? Okay. Now next two reduction reactions. One is your Clemenson and second one is your Wolff-Kishner. Basically, both are reduction reaction. In this reduction reaction, from the carbonyl component mainly, you can use either aldehyde, you can use either ketone, whatever you are using, no problem. But one reaction is catalyzed by acid and second one reaction is catalyzed by the base. Here actually in this case, zinc actually trapped in mercury. This is called zinc amalgam. This zinc, this has also have the Lewis acid property, and in the first stage, zinc will trap this chlorine to form ZnCl2. And by the same fashion, in the first stage, nascent hydrogen generated. And this nascent hydrogen will attack on this polar system. Polar system means CO system. And by this way, this oxygen get replaced and you will get this alkane system. So in the ATAD reaction, you notice that from the toluene, we came here. And in the Clemenson reduction, just opposite process. So you can say this reaction is ATAD and this reduction is your Clemenson, this reaction. So Clemenson reaction, student, and your ATAD reaction are just opposite. Okay. In one reaction, you can generate aldehyde from the hydrocarbon, and in the second reaction, means in the Clemenson, opposite thing means reduction happen. Okay. Now Wolff-Kishner reaction is same, means it's a reduction, but based on alkali. It was based on acid. This is based on alkali. Look at this. In the first stage, hydrogen used. This hydrogen actually eliminates the water molecule. In the next stage, in the presence of this KOH, there is rearrangement happen. Look at this. Starting material was your carbonyl compound. It might be aldehyde, might be ketone, anything. Now, in the next stage, after attacking this hydrogen and this oxygen gets eliminated, means water molecule get eliminated. In the next stage, this C double bond N, this NH2 form. Actually, in the next stage, approximately 180 degrees centigrade heat required, this heat, and this KOH means in the presence of this alkali, rearrangement happen. And this nitrogen in successive step actually produce this nitrogen gas, this N2 system. And this C part with this CH2 will produce this hydrocarbon. So basically, basic difference between Clemenson and Wolff-Kishner is the medium. The target is same. The target is the production of the hydrocarbon from the carbonyl component. Any question, anyone? Any question? Well, now next, tolerance and failing. I am not discussing because everybody did this test. I will just explain about tolerance test. This is why it is used for basically. Normal, whenever in our practical laboratory, when organic group detection happens, so organic compound, first we usually target or usually do the 2,4-DNP test. If this 2,4-DNP test is giving you the positive result, you assign that might be a carbonyl compound. Otherwise, if it's a no, then other than carbonyl, might be alcohol, might be carboxylic acid, might be any another group. I am not discussing about this. So if 2,4-DNP test means the Brady's reagent give you the orange color crystal or orange color precipitate, then you assign that it might be carbonyl group, might be aldehyde or might be ketone. Now after this, if you perform this tolerance test, tolerance reagent is made by when silver nitrate solution in the first stage, in the first case you add drop by drop NaOH and turbidity appeared. After that, you successively add ammonium hydroxide cautiously. and shake it completely. Up to that, the turbidity disappears. And finally, you will get one colorless solution of this component. And this is nothing but your Tollens reagent. And this Tollens reagent is used as the mirror, okay, the mirror formation test or the mirror test inside the inner wall of the test tube, this test. So if Tollens test may give you the positive result, yes, or maybe no. If you are getting the positive result, yes, then nothing but this is an aldehyde. Otherwise, if it's a no, fail, then it's a ketone. This is the test by which or you are used used in your laboratory to separate between aldehyde and ketone. Next one is the failing test. The same thing means normally here copper sulfate. This is the failing A, and failing B is normally used here actually the Rochelle salt basically, or sodium potassium tartrate something is used as a failing B. This is the mixture of equal volume basically. So here the attacking agent nothing but is copper 2 plus from copper sulfate, and the 5OH minus is from your Rochelle. So RCHO basically the aldehyde present, this one actually by on it aldehyde, this test is performed. And result might be two things, means either positive or might be negative, same fashion where you use. So either might be it's a positive yes or might be no. If it's a yes, then aliphatic aldehyde present, and if it's a no, then aromatic aldehyde present. These reagents are basically used, I think, during the practical, because practical is already final practical exam is already scheduled. I think you are preparing well with the Tollens and failing, so I'm not discussing details about this reagent. I'm just only discussing where actually you use these two reagents. Okay, I'm coming in next slide because we have limited time. Main reaction is the aldol reaction. This is very important for your exam. Why the name aldol? I think everybody knows the aldol is actually here the starting material is nothing but one carbonyl component contain the alpha hydrogen. Now some of the students are confused what is alpha carbon. So the adjacent carbon of the carbonyl group is known as the alpha. And the alpha carbon, if contain hydrogen, that is called alpha hydrogen. So if alpha hydrogen present by the CHO groups minus R effect, these hydrogens are sufficiently acidic. And since they are already acidic, approximately if you are using 10% NaOH or only 50% BaOH whole 2, means weak base, then you can start this reaction. And by this reaction, the specialty is carbon-carbon bond is formed. So basically in this case, what happened? In this case, look at this what happened. I am starting with one carbonyl compound, that is your acetaldehyde, and second component is CH2, one hydrogen, CHO. What happened? Do you know? This hydrogen will be connected or transferred to with this oxygen, and this carbon will connect with this carbon. This is the main motto or main theme. Okay, and by this way you will get CH3, the CH, this is CH, this OH, this CH2, CHO, this is the product. But if you put heat on it, then from the CHO group already present will operate minus R effect. Okay, so these hydrogens are sufficiently acidic here. Okay, so these hydrogens and this OH will eliminate H2O, and you will get CH3, CH, double bond CH, CHO, one unsaturated product. And this unsaturation product formation happen by the elimination of water, that is the dehydration. So this is called condensation reactions. And aldol is this one, not this one. Why this is called aldol? Because the product, notice please student carefully, you can notice this one also. From your starting material, your carbonyl compound, you are getting all here and carbonyl compound. Here is a carbonyl compound aldehyde and all here. That's why this compound is your aldol. And this compound is not aldol. This is condensed product of your aldol. Okay. So this reaction is so crucial, so important. Any question, anyone? Any question, anyone? Oh, no. Okay. Now I am coming in cross aldol reaction. This is another important reaction. Cross aldol reaction here actually, you will use two different substrates. One is this, one is this, and both of them have alpha hydrogen. Look at this CHO group, this CHO group, this is alpha, this is alpha. So we will get four different products. I am marking this is as A, this is as B. Now products might be A and A. This is the self condensation of A. Now B might get or give the same set of product BB. And second case is AB. AB means here the B system means if I am assigning this one is the B, B is the H plus donor and A is the H plus acceptor. This is the reaction. So basically, this aldol reaction is happening via proton transfer, H plus transfer. And the fourth product will be the BA, where A is the donor of H plus and B is the acceptor of H plus. This reaction is called your cross aldol. But in reality, this reaction is not actually performed. Why? Because if you perform this test, you will get four different products with very less percentage yield, and that will be one problematic idea. Okay, that's why in reality, how it's done in reality in the practical aldol, which is also called the Claisen-Smith reaction, what happened? One aldehyde you have to choose or one carbonyl you have to choose which contain alpha hydrogen, and another carbonyl that should not have any alpha hydrogen. And normally you have to take like this. You are taking one conical, let's think about. In this conical, you have to take one carbonyl component have no alpha hydrogen. That is your CHO, might be. And you have to take this one with alkali, NaOH. And you have to add drop in it, the carbonyl component having alpha hydrogen. Then you will get better percentage yield and single product. Okay, this is called the practical aldol or Claisen-Smith reaction, not included in your syllabus. Okay, but just still I just mentioned here. Any question, anyone, please? No. Okay. Now next important reaction is the Cannizzaro reaction. This is from the aldehyde and main reaction. Most of the time, the question usually alternatively asks from either aldol or Cannizzaro. From that perspective, this is very important. But little bit difference is here the starting material means the carbonyl compound. Both of the carbonyl compound no alpha carbon or no alpha hydrogen. This one, respect to this one, this is alpha carbon, but here no alpha hydrogen present. So starting material is the carbonyl compound having no alpha hydrogen. And since no alpha hydrogen, the base is concentrated or at least 50% NaOH you have to take or 50% KOH you have to take. Okay. And this reaction, by this reaction, one component will oxidize to corresponding carboxylic acid, and another component will normally give you the alcohol. And this reaction happen via hydride transfer, means H minus transfer. That means from this system, if you notice, this hydride is shifted in this system to give you CHHH. So CHHH. Okay. And this O become hydrolyzed to OH. On the contrary, this part COH. So HCO. This OK part is actually coming from this one. Okay. So basically, this reaction runs via hydride transfer. On the contrary, aldol reaction runs via proton transfer. And since here no free or acidic proton present, the concentration of the base is high. And another important parameter is here simultaneously from carbonyl compound oxidation happen to form carboxylic acid salt, and here the carbonyl compound is generating another alcohol. You can see this is also the benzaldehyde is forming this benzyl alcohol. This process is nothing but your reduction where H minus is trapped, and second one, this second molecule is giving you the sodium benzoate on the oxidation reaction. Okay, so this is simultaneous oxidation reaction, or sometimes this is called disproportionation reaction, means a reaction from the set substrate. When oxidation reduction happen, they are called your disproportionation reaction. You can solve this question. Okay, this is the application of this one. Now, this is shortage of time. I'm going throughout. Now this HVZ reaction is from your carboxylic acid chapter, and this is applicable for the formation of one example, lactic acid. Sometimes the question asked in your exam, produce lactic acid from the acetic acid. So formula of acetic acid is this, and formula of lactic acid is this one, means, sorry, CH3 you have to here, not acetic acid. CHOH COOH. Basically, here the starting material is nothing but a substrate which contain the alpha carbon hydrogen. The substrate is nothing but carboxylic acid. This contain alpha, okay, at least one alpha hydrogen. And in the presence of red phosphorus and X2, where X is mostly chlorine and bromine, not the iodine and fluorine. I'm not taking about that much time about the thermodynamical comparison. So basically, red B in the presence of X2 means Cl2 or Br2, you will get an alpha halo substituted product, means alpha halo carboxylic acid. So if your starting material is propanoic acid actually, and you are going with this red P and X2, in the intermediate state, you will get the product H3C CHX CH2. And finally, from this to this, if you hydrolyze, because this is acid, so in the acid medium, if you hydrolyze, this X will be replaced by the OH, and this is nothing but known as your lactic acid. So this reaction is the very important for the formation of lactic acid. Now you can see this question. HVZ reaction is used to prepare which one? Option A, option B, option C, option D. Obviously, for the formation of alpha halo acid, because this is your group respect to this in the second carbon, alpha halogen is forming. So answer will be your alpha halo carboxylic acid. Now next reaction is very important for your exam. Okay, I'm not saying to go step by step, only initial and final stage I'm suggesting you. Okay, now here, this is called Gabriel thalamide synthesis. Why this is important? This is important for the formation of only primary amine. That means by this process, you can get only primary amine. This is your starting material, thalamide, which is synthesized from phthalic acid, dehydration, then followed by ammonia. Okay, then you are getting this, you got this thalamide. Whenever this thalamide, due to this conjugated COs, strong minus R operation, this hydrogen become sufficiently acidic. So whenever you are treating with base, you will get these kinds of system. And in the SN2 reaction, you will get this one. And finally, in the hydrolysis, you will get your 1 degree product. So student, do not frighten about it. Only you have to write thalamide, then KOH, RX, hydrolysis, the final product. Okay, don't go with the step-by-step formation. So this reaction, Gabriel thalamide synthesis, is important for the formation of 1 degree amine. Sometimes the question usually asked in your exam that why Gabriel thalamide synthesis is so important. This question means for the formation of 1 degree. Sometimes assertion reasoning type question come that by the Gabriel thalamide synthesis we can form 2 degree, 3 degree amine. The statement is correct or wrong, you have to explain this kinds of question. Okay, the question is given here. But one thing you should have to remind that since the reaction is running via SN2 reaction, so obviously aromatic amine you can synthesize. Only you can synthesize the primary amine by this process. Because in the last slide, if you notice, this reaction is nothing but, this reaction was SN2 reaction, this reaction here, which is SN2. So if you are using here benzene like X, means you want to synthesize aromatic system, then SN2 reaction means backward side attack is not possible, as I told you, as I think everybody knows it properly. So next 2 reactions are actually, one is called step down reaction. Step down reaction is your Hofmann, sometimes it's called Hofmann degradation or Hofmann bromamide degradation. The name actually bromamide is coming from because starting material sometimes bromoamide. Okay, so starting material is nothing but one amide in the presence of Br2 and 4 molecule of the NOH. This is important, 4 molecule, because sometimes question asks how many molecules is essential for 1 molecule of the amide conversion into 1 molecule of the ammonia. That from that perspective, this is very important. So here by this way, this primary amine is synthesized, and look at this CO step down happened. So this is important for 1-degree amine synthesis and also for the step down process. So you can follow this question. This question is taken from the sadhana program. You can go through it. Carbylamine reaction sometimes asked. This is actually the uh, detection reaction or identification reaction of 1-degree amine, not for the, it is utilized for the 2-degree and 3-degree amine. Now, in any mixture system or any mixed system, or let's think about in 3 test tube, primary, secondary, tertiary amine present, then if you are using this chloroform and this KOH, this chloroform and this KOH, then you will get one isocyanide compound. And this is possible only for the 1-degree amine, not for the 2-degree and 3-degree amine system. So I'm not going with Hinspark because this is not exactly the name reaction. This is a test to segregate between 1-degree, 2-degree, and 3-degree amine. And the last reaction of this is your coupling reaction. This is most important. And the coupling reaction is nothing but when the starting material will be your benzene diazonium salt, that is benzene diazonium chloride or benzene diazonium bromide, in the presence of any kinds of alcohol, aromatic alcohol, might be naphthol, might be your phenol, etc. Then in the presence of alkali, okay, in the para position, normally this N double bond N system coupled actually. And what this is reaction is so important because this reaction is important for the perspective of synthetic dye. Normally these dye are used to fabric your actually colorful cloths. That's why by the variation of this group and this group, different color dye means orange, red, green, these kinds of dye is formed. So basically in this reaction, diazonium salt in the presence of alkali and little bit of cold condition. This one is coupled. The first stage, this is ice cold condition, not this one is ice cold condition. In the second stage, you will get this diazonium salt. From this diazonium salt, this is the question you can go through. Rajkumar sir, hello, 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 hello. So actually, students, I will take only 5 minutes. That is mechanism part. 5 mechanisms are there, but I included only 3 mechanisms, which are more important. Okay, since time are not uh, giving that much permission, so I'm just going just through out of these 3 reactions. One is the ethylene to ethanol. Second one is ethanol to ethylene, and third one is the addition of the HI in the ether system. So first is your ethylene to ethanol. This reaction runs via 3 steps basically. In the first stage, this is called your protonation stage. Normally, ethylene actually accepts one proton by its pi density and produces this intermediate. In the second stage, second stage. The second step is the attack on the carbocation. So this step is the formation step, first stage of the carbocation. So this step is slow and rate determining stage. And in the next stage, if you notice, the next step is nothing but the addition of the water step on the carbocation. Since the carbocation form in this case, the water molecule can attack from the top side as well as from the bottom side to form this one. And in the last stage, the elimination of the proton, which is trapped in the first stage, because the supplier of this H plus is the catalyst. Means the acid basically. Mostly diluted sulfuric acid is used for the for these kinds of water addition basically. So in the last stage, this water molecule will trap this H plus proton actually to form the intermediate, to form the final product is your alcohol and your final H3O plus. So basically here in the first stage, the H plus, this H plus was given from the acid. In the last stage, again, it's returned back. So basically this hydrolysis reaction, this water addition reaction in the alkene system, okay, runs via carbocationic intermediate. And since this is applicable for the ethylene actually, so this reaction, I am not saying it is nothing but your addition reaction, means it's your okay. So basically this reaction, please follow it. I'm not going with more elaborate discussion. And next one is your ethanol to ethylene, this reaction. So ethanol to ethylene, just opposite reaction basically happen. The first stage, it also happen in 3 steps. First stage is the proton trapping stage or the proton acceptance stage. And in this supply of this proton is from the concentrated sulfuric acid. As you know, this reaction alkene form, normally this reaction is running in the 443 Kelvin temperature. But if you are going with 413 Kelvin temperature, the reaction will give you another intramolecular dehydrating, that is dehydrating product, that is called your ether. Now in the first stage, the protonation stage, the protonation happen in the fast way from the H plus. The next stage is the carbocation formation stage. This is the intermediate formation stage and slow stage. In this case, what happened? In this case, after the trapping of this H plus, this oxonium type ion form. This oxonium ion in the next stage eliminates the water molecule to produce one carbocation. And that carbocation in the last stage actually eliminates its corresponding the next adjacent carbon 1H plus. And this H plus which is eliminated in this case trapped in the first stage. So you can say this is nothing but acid catalyzed dehydration, but this dehydration happen in a single molecule. So at the 443 Kelvin temperature, this dehydration is nothing but intramolecular dehydration, not intermolecular dehydration. And you can get this information for a little bit for more why intramolecular, how it's happened and all. And the last presentation is of this is the addition of HI in the ether system. This is also important. Basically, this reaction also runs in normally in 2 to 3 stages. In the first stage, actually, the proton trapping happens from the strong HI system. Normally, the lone pair of the oxygen is sufficient to trap this proton. And in this first case, this intermediate is formed. Actually, this intermediate is formed. I'm mentioning here with the mark. In the first stage, the lone pair of the oxygen trap the H plus from the strong acid HI. Actually, here the iodine is a good living group due to its bigger size. And in this case, basically, I minus gets eliminated in the first stage. And here after this formation, one simple SN2 reaction happened by this I minus, because here the reaction is running via concentrated HI, not in diluted system HI. So basically, I minus will go in SN2 reaction. This is the SN2, and this bond of the oxygen will switch towards this adjacent corresponding oxygen, and you will get the product of corresponding lower substituted iodide means halide system, and the higher carbon means higher degree system, 2 degree, 3 degree system will give you the corresponding alcohol. Okay, I am not going discussing about this one. Most of the time, the question usually asked about this one. Means for the formation of, let's think about you want to give the product, or you want to get the product from this and this substrate. Okay, or write the product. This question is very important. Give the major product form with the addition of the HI for this one and this one. Normally, either this bond will clip or this bond will clip. Or here for this one, either this bond will clip and this bond will clip. Since the reaction is running via SN2 pathway, actually, so you have to choose such a way that the substituent here, look at this. This substituent is nothing but your 1 degree substituent. So this 1 degree substituent will have to set with iodide. That's why the alkoxide from this side, left hand side, this lone pair will eliminate this iodide minus. If you choose the opposite choice, that means instead of this, if you choose this, this is OH and iodine here, this is not possible, because this due to its backward side steric hindrance, it's not possible. But for this one, the scenario is little different. Why is little different? Because if you are considering this one as a carbocation, that means this reaction is not following the SN2 pathway. Here, this carbocation, this reaction will run via this carbocation formation. So carbocation will be stabilized by the conjugation of this benzene or benzene ring lone pair. And by this way, whenever this plus form, obviously I minus will be connected with this system, and on the counter side, this OH will be connected with OH system. Now, student, you can go with this all practice questions. These are for your practice, for your enrichment. What I discussed, all these questions are given here. All the questions are actually taken from the Sadhana program, and from the some previous year question, model question paper from the CBSE. So in terms of next exam from the pre-board, for the pre-board 2 and for the next year final exam, these questions are important. So my suggestion, please follow these questions and you can take the help of your teacher. And if any feedback, anything is you are thinking that you want to give for me, you are always welcome. Thank you. Have a nice day.